Hi everyone. Today the topic is Chemical Engineering Thermodynamics Basic Concepts Part 4. First topic is enthalpy. So enthalpy is the measurement of energy in a thermodynamic system. So what is the energy in a thermodynamic system that can be measured by the term enthalpy? So here the quantity of enthalpy equals the total heat content of a system, which is equivalent to the system's internal energy plus the product of volume and pressure. So mathematically, if you can represent the enthalpy, it is equal to the sum of internal energy and the product of pressure and volume of the system. So here enthalpy is indicated by H, internal energy by U, pressure by P, and volume by V. So H is equal to U plus PV. So here enthalpy is a state function and extensive property. Its unit is joule per kg. So energy per mass units. So the next one is, so here we can represent the enthalpy in a diagram. So the sum of internal energy and the energy required to create a new volume. So here you can see a piston cylinder assembly. So in this, the system is ideal gas and we have taken the surroundings. So the heat supplied to the gas increases the internal energy. So whatever heat we are supplying, it increases the internal energy and then the gas will expand and create a new volume. So in the first diagram, you can see the heat is being supplied to the gas. And in the second diagram, we can see the expansion of the gas, which creates a new volume. So the piston cylinder assembly, it will be raised to certain height, which is creating a new volume. So this is the representation of enthalpy. So from this, we can say H is equal to internal energy plus PV. That equation we can represent. Next one is entropy. Entropy is defined as a measure of randomness or disorder of a system. The greater the randomness, the higher the entropy. So if you increase the randomness, entropy will be increased. So this entropy is also a state function and extensive property. This unit is joule, joule per kilomole. So for example, the entropy of a solid where the particles are not free to move is less than the entropy of a gas where the particles will be free to move. We will fill the containers. See here we can see that. So here we can represent the entropy of solid, liquid and gas. So solid, it's a less randomness, so less entropy. And if you go for the gas, it will be more randomness, it will be more entropy. Between these two, we have liquid, which is having a medium randomness, which is having medium entropy. So delta S will be, delta S is greater than 0 and reversible delta S is less than 0. So S represents the entropy, delta S represents change in entropy. Next one we see ideal gas. An ideal gas is defined as one for which both the volume of molecules and forces between the molecules are so small that they have no effect on the behavior of the gas. So an ideal gas can also be represented as which follows the ideal gas equation of state, namely PV equal to N or T. Similarly, we can represent real gas. The term real gas usually refers to a gas which doesn't behave like an ideal gas. So real gases or non-ideal gases whose molecules occupy the space and have interactions. Consequently, they do not adhere to the ideal gas law. So both ideal gas and real gas can be represented like this. You can see the basic differences in real gas and ideal gas. So real gas particles will be having volume, energy lost in collisions, and they have intermolecular forces. Ideal gas particles have no volume, collisions are elastic, and no interactions between the particles. So real gases will behave like ideal gases at certain conditions. Those conditions are at high temperatures and at low pressures. The real gases will behave like ideal gases. So these ideal gas conditions we can use in thermodynamic problems. So whether it is ideal gas or real gas, based on that we will be doing many calculations of thermodynamic problems. So here this is the today's topic. If you like my video, please subscribe my channel. Please like, share and comment my videos. Thank you very much.